For thousands of years, humanity has looked toward the sky and asked one of the oldest questions imaginable. Are we alone? The universe contains hundreds of billions of galaxies, each filled with billions of stars. Many of those stars have planets. Some may even have conditions suitable for life. And yet, despite centuries of searching, we still have no confirmed evidence of life beyond Earth. But what happens when something appears in our skies that we cannot immediately explain? A strange object, an unusual movement, a signal that does not fit our expectations. The first instinct is often to ask, what is it? But science asks a different question. What evidence do we have? Because throughout history, the greatest discoveries have not come from assumptions. They have come from better observations. Galileo's telescope revealed worlds invisible to the naked eye. Radio telescopes uncovered an invisible universe. Space telescopes allowed humanity to look deeper into cosmic history than ever before. And now, a new scientific effort is asking a very modern question. Can we build instruments capable of investigating the unknown? This is the story of the Galileo Project. For decades, reports of unusual objects in the sky have existed across the world. Some were later explained. Aircraft, satellites, weather balloons, atmospheric effects, camera artifacts. Human perception is remarkably good at recognizing patterns, but it can also be easily misled. A distant object can appear to move faster than it really is. A reflection can appear like a physical object. A small object close to a camera can appear enormous in the sky. This is why science requires something more than observation. It requires measurement. A witness report can tell us that someone experienced something unusual. A video can show us that something was recorded. But scientific investigation requires additional information. How far away was it? How fast was it moving? What was its temperature? What materials was it made of? Was it producing signals? Could another independent observer detect the same thing? Without those answers, the mystery remains. Not because the object is necessarily extraordinary, but because the evidence is incomplete. This challenge is not unique to unidentified aerial phenomena. Science has faced similar situations throughout history. Before microscopes, the world of bacteria was invisible. Before telescopes, the moons of Jupiter were unknown. Before advanced detectors, gravitational waves were only theoretical predictions. The universe has always contained discoveries waiting to be made. The limitation was never reality itself. The limitation was our ability to observe it. Astronomer and science communicator Carl Sagan famously summarized the scientific approach with a phrase that has become closely associated with extraordinary discoveries. Extraordinary claims require extraordinary evidence. The meaning is simple. The more remarkable a claim is, the stronger the evidence must be. But that statement does not mean extraordinary discoveries are impossible. History is full of them. It means that when something challenges our understanding of reality, the solution is not belief. And it is not rejection. The solution is better evidence. For many scientists studying unexplained aerial phenomena, this has always been the central problem. Not a lack of stories. Not a lack of interest. A lack of scientifically collected data. And that question became even more important in 2017, when humanity encountered something it had never seen before. A visitor from beyond our solar system. On October 19, 2017, astronomers using the Pan-STARRS telescope in Hawaii detected a faint object moving through the solar system. At first, it appeared to be another small body among millions. But calculations soon revealed something extraordinary. This object was not orbiting the Sun like a normal asteroid or comet. Its path showed that it had come from outside our solar system. Humanity had discovered its first confirmed interstellar visitor. It was named One-Eye Oumuamua, a Hawaiian name often translated as a messenger from afar arriving first. And for astronomers, that name was fitting, because Oumuamua was the first natural object known to have traveled between stars before passing through our cosmic neighborhood. But almost immediately, scientists noticed something unusual. Oumuamua did not behave exactly like familiar objects. Its brightness changed significantly as it rotated, suggesting an unusual shape. Its trajectory showed a small additional acceleration as it moved away from the Sun. For a comet, this could be explained by gases escaping from its surface. But observations did not reveal the typical signs of cometary activity. No obvious tail. No large cloud of dust. No clear explanation that answered every question. Scientists proposed several possible explanations. Perhaps it contained unusual materials. Perhaps hidden gases escaped from its surface. Perhaps sunlight itself was responsible for the acceleration. Each idea attempted to explain the available observations using known physics. But the object remained unusual, and that uncertainty created one of the most interesting scientific discussions of recent years. Among those studying Oumuamua was Harvard astronomer Professor Avi Loeb. Loeb argued that one possibility deserved consideration. Could the object's unusual properties be consistent with something artificial? This was a controversial suggestion. Many scientists preferred natural explanations. Others argued that all possibilities should remain open until the evidence ruled them out. But the larger lesson was not about whether Oumuamua was artificial or natural. The larger lesson was this. Humanity had detected its first known visitor from another star system. And we were not prepared. By the time we discovered it, it was already leaving. Perhaps the most important question was not, what was Oumuamua? But, if another object like it appeared tomorrow, would we have the tools to study it properly? That question would inspire a new scientific project. A project built around a simple idea. If better evidence is needed, then we need better instruments. Why would a modern scientific project searching for unexplained objects in the sky be named after a scientist who lived more than 4 centuries ago? The answer is not about history. It is about a way of thinking. In the early 17th century, humanity believed it already understood the universe. The Earth was considered the center of creation. The heavens were thought to be perfect and unchanging. These ideas had existed for generations. But there was a problem. Humanity had never possessed the tools needed to properly test them. Then, a mathematician and astronomer named Galileo Galilei pointed a telescope toward the sky. And the universe changed forever. Galileo did not invent the telescope. But he understood something revolutionary. A telescope was not just an instrument for seeing farther. It was an instrument for discovering things humanity did not know existed. When Galileo observed the moon, he saw mountains and valleys. The moon was not a perfect celestial sphere. When he observed the sun, he saw dark spots moving across its surface. The sun itself was changing. But perhaps his most important discovery came when he observed Jupiter. He discovered 4 objects orbiting another world. Today, we know them as Jupiter's largest moons: Io, Europa, Ganymede, Callisto. Their existence revealed something profound. Not everything in the heavens revolved around Earth. A simple observation challenged centuries of assumptions. The lesson was clear. Science advances when better instruments allow us to see reality more clearly. That pattern has repeated throughout history. The microscope revealed a hidden world of cells and microorganisms. Radio telescopes revealed invisible signals from across the universe. The Hubble Space Telescope transformed our understanding of galaxies. The James Webb Space Telescope is now allowing scientists to observe some of the earliest chapters of cosmic history. Each generation expands the frontier of knowledge by building better tools. This is why the name Galileo carries such meaning. The Galileo Project is not named after Galileo because it expects to find something extraordinary. It is named after Galileo because of the method he represented. Observe, measure, test, follow the evidence wherever it leads. The project begins with the same philosophy that changed astronomy centuries ago. Do not start with a conclusion. Start with a question. What would we discover if we had better instruments watching the sky? And this brings us to the heart of the Galileo Project. Because ideas alone are not enough. Scientific questions require scientific tools. And the Galileo Project's answer is a new type of observatory. One designed not for a predictable target, but for the unexpected. Traditional astronomy is built around known targets. Astronomers point telescopes toward planets, stars, galaxies, nebulae. They know where these objects are. They know when to observe them. But unidentified objects create a completely different challenge. They appear without warning. They may last only seconds. And once they disappear, the opportunity may never return. The Galileo Project was designed around this problem. Instead of waiting for a mysterious object to be reported, the goal is to continuously monitor the sky with scientific instruments designed to capture reliable data. The principle is simple. A single image rarely tells the complete story. A light in the sky may look unusual, but without knowing its distance, its speed cannot be accurately calculated. Without knowing its temperature, its physical nature remains uncertain. Without environmental information, atmospheric effects can be mistaken for something more unusual. This is why the Galileo Project uses multiple types of sensors working together. Optical cameras capture visible light. They record what the human eye would see, but with greater precision. Infrared sensors look beyond visible light. They measure heat signatures. An aircraft, a drone, a satellite, a natural object. Each may leave different thermal patterns. Radio instruments monitor the electromagnetic environment around the observation. They help determine whether an object is associated with known communication signals. Weather sensors provide essential context, because the atmosphere itself can create surprising visual effects. But perhaps one of the most important tools is not a camera. It is artificial intelligence. Modern observatories generate enormous amounts of data. A human team cannot manually examine every frame. AI systems help identify familiar objects. Aircraft, satellites, birds, balloons, atmospheric effects, camera artifacts. The purpose is not to search specifically for extraordinary explanations. The purpose is to quickly separate what is known from what remains unknown. This distinction is extremely important. The Galileo Project is not designed to prove that every unusual observation represents something extraordinary. In fact, the majority of observations are expected to have ordinary explanations. That is exactly how science works. A good investigation does not begin by asking, "How unusual is this?" It begins by asking, "What does the evidence actually show?" The true innovation of the Galileo Observatory is not any individual sensor. It is the combination of many independent measurements. Because the strongest evidence does not come from a single dramatic image. It comes from a complete scientific record. Multiple observations. Multiple instruments. Multiple ways to test the same event. For decades, many unexplained sightings lacked this type of information. The Galileo Project attempts to change that. It replaces incomplete observations with measurable data. And whether the final answer is ordinary or something truly unexpected, the evidence will decide. But building instruments is only the beginning. A natural question remains. What has the Galileo Project actually discovered? Has it found evidence of something extraordinary? Or is its greatest contribution something different? Because in science, sometimes the most important discoveries are not the answers. Sometimes they are better questions. When the Galileo Project was announced in 2021, it attracted worldwide attention. Many people expected dramatic discoveries within months. Some hoped for confirmation of extraordinary phenomena. Others predicted the project would find nothing at all. But science rarely works on either timetable. Before researchers can investigate the unknown, they must first understand the known. That means collecting enormous amounts of data, testing instruments, calibrating sensors, verifying that every observation can be trusted. It is careful work, often invisible to the public. But it forms the foundation of every scientific discovery. Every clear night, the observatory records thousands of objects moving across the sky. Most turn out to be entirely familiar. Commercial aircraft, satellites reflecting sunlight, meteors burning up in Earth's atmosphere, birds, insects passing close to the cameras, even subtle atmospheric effects. Each identified object becomes part of an ever-growing reference library. And that library is one of the project's greatest strengths. Because every ordinary object successfully identified makes future investigations more reliable. The unknown becomes easier to recognize only after the known has been carefully understood. This may sound less exciting than discovering something extraordinary. But in science, it is exactly how progress happens. Consider medical research. Before a doctor can recognize a rare disease, they must first understand thousands of common conditions. Astronomy is no different. To recognize something genuinely unusual, researchers must first eliminate everything ordinary. The Galileo Project was designed with this philosophy at its core. So, has the project found evidence of extraterrestrial technology? At the time this documentary was produced, no. It has not announced verified evidence of alien spacecraft or non-human technology. That answer may disappoint some viewers. But it should not be surprising. The project's purpose has never been to prove a particular conclusion. Its purpose is to build a scientific framework capable of testing extraordinary claims with extraordinary evidence. In many ways, that framework may become its most enduring contribution. Perhaps the project's greatest success so far is not a discovery. It is a demonstration. A demonstration that unexplained aerial phenomena can be investigated using the same scientific principles applied everywhere else in astronomy. Careful observation, independent measurements, repeatable methods, transparent analysis. Whether future discoveries are ordinary or revolutionary, the method remains the same. History reminds us that major scientific breakthroughs are often preceded by years of preparation. The Laser Interferometer Gravitational Wave Observatory, better known as LIGO, spent decades refining its instruments before detecting gravitational waves. The James Webb Space Telescope required years of testing and calibration before transforming astronomy. Large scientific projects are measured not in weeks, but in years. The Galileo Project is still in the early stages of that journey, and its most important discoveries may still lie ahead. Of course, not everyone agrees with the project's approach. Some scientists believe its goals are essential. Others remain unconvinced. And that disagreement is not a weakness. It is one of science's greatest strengths. One of the most common misconceptions about science is that scientists always agree. In reality, scientific disagreement is both normal and necessary. Every significant scientific idea is questioned, tested, challenged, sometimes rejected, sometimes strengthened. That process is not a flaw. It is how science protects itself from error. The Galileo Project has generated exactly this kind of discussion. Supporters argue that unusual aerial observations deserve rigorous scientific investigation using modern instruments. If unexplained events exist, they believe they should be studied objectively rather than ignored. Critics agree that scientific investigation is valuable, but question whether the available evidence justifies dedicating significant resources to the search. Others argue that natural explanations remain overwhelmingly more likely for most observations. These are reasonable scientific disagreements, because they concern probabilities, not possibilities. Professor Avi Loeb has often argued that scientists should be willing to investigate even unlikely hypotheses if the evidence warrants it. Many of his colleagues agree with the importance of investigation, while disagreeing with some of his interpretations. That distinction matters. Science is not a contest between believers and skeptics. It is a conversation about evidence. Different scientists can examine the same data and reach different provisional conclusions. As new evidence becomes available, those conclusions evolve. This brings us back to Carl Sagan's famous observation: extraordinary claims require extraordinary evidence. The Galileo Project embraces that principle, not by assuming extraordinary explanations, but by attempting to collect evidence capable of testing them. If future observations support conventional explanations, science advances. If future observations reveal something unexpected, science advances. Either outcome increases our understanding of reality. That is the true objective. Perhaps this is the project's most important lesson. Curiosity and skepticism are not opposites. They are partners. Curiosity encourages us to ask difficult questions. Skepticism ensures we demand reliable answers. Together, they form the foundation of scientific discovery. For centuries, every generation has built better instruments to explore the unknown. Sometimes they confirmed what humanity already believed. Sometimes, they changed history. Whether the Galileo Project ultimately joins that list, only time and the evidence will tell. At the Unknown Frontier Media, we don't tell you what to believe. We explore the evidence, examine the science, and invite you to draw your own conclusions. Until next time, keep looking up, because the greatest discoveries may still lie beyond our horizon.